Hey, welcome back. It's Darren from the Industrial Revolution channel. This is part 5 of our 7-part course in understanding early steam power and atmospheric engines. If you're just joining and you want to jump back to the beginning, there should be a link showing up here on the screen. And if not, check down the description. Anyway, we just finished taking a look at this canal pump from James Watt here. And absolutely huge. It's really hard to get this entire thing actually on camera. But as I mentioned earlier, compared to the Newcomen engine, there's really only one change. Let's take a closer look at that. So as we move in on this pump, here's the giant beam at the top and the chains and the pump shaft. But down behind the pump shaft is what really made James Watt's name for him. This is a slightly more advanced version. His first version just had a single cylinder. Single separate cylinder, the water jet was moved to there. He did later realize that he could actually use a cylinder which was actually submerged in water, so this would have been filled with water, and combine it with a vacuum pump to pull the condensed steam and any uncondensed steam or air out of the cylinder. That actually allowed it to be still more efficient than his earlier version. So that's really the only change that Watt made from Newcomen's 1712 engine to this later canal pump. Shows just how good the Newcomen design over here actually was. So compared to the Newcomen engine, that external condenser is really the only change that was made here. Just about everything else here is the same. Engineering's improved a little bit, the valves have improved a little bit. But essentially you're running the same plug tree, you're running the same type of cylinder, you're running the same kind of everything here, except for that condensing cylinder. So this doesn't really have many changes from that Newcomen engine. This is still an atmospheric engine, still runs the same way. But that one change made James Watt famous and launched his career. So we've looked at a couple of colossal atmospheric steam engines here, and you've probably been asking yourself, why didn't they just use higher pressure steam? These ran at about 5 psi of steam, and look, Watt and Newcomen were both really smart guys. They both knew there was no question higher pressure steam would have worked better, would have allowed for smaller, more powerful engines, but they were held back by this. This is a Haystack boiler, and really until the early 1800s, this is all they had to make steam. It's a fairly simple boiler. It's a giant metal ball. You lit a fire in the bottom. The fire would then have the flames and the exhaust gases would circle around inside of this heavy brick structure to expose the outside of the ball as much as possible, to get as much heat as possible from it, before finally exhausting out through the smokestack here. As I mentioned earlier, these were initially hand-hammered plates, hand-riveted together, and they just couldn't really go any higher than about 5 psi because they'd tend to blow up. Because of that limitation, because they were stuck with this as the only boiler tech, really until the Cornish boiler was invented, they had to use atmospheric engines. And they did, and they worked really well. So when you're working with pistons like this, it really doesn't make any real difference what your actual pressures are until you get up to really high pressure, then it starts to matter. So all that really matters is the pressure on top of the piston versus the pressure on the bottom of the piston. What's that difference? That difference is what will give you your force. So if you put 5 psi above ambient at the bottom and you have ambient on the top, you'll go up. If you have 5 psi more on top, you'll go down. And one of the things that confuses a lot of people about atmospheric engines is that there's not one, but 2 references to pressure. They don't agree with each other, and they use exactly the same terminology for them. You have ambient pressure, which is Oh, it's about 15 psi or 1 bar. Um, that is, it varies with elevation, it varies with altitude, it varies with the weather. That 1 psi, it's actually like 14.5 psi typically. I just use 15 on this channel just to make math and numbers easier. And that's above absolute vacuum. But when you say the boiler is producing 5 psi of steam, what you're really saying is it's producing 5 psi on top of the 15 psi. So the above vacuum, you're actually generating about 20 psi above vacuum, about 5 psi above ambient pressure. And that's where people tend to get confused. So with an atmospheric engine here, the top of the cylinder, this is always 1 atmosphere of pressure. It's always about 15 psi. The bottom, when you fill it with steam, that can go up to as high as 20 psi above absolute vacuum. Absolute vacuum is what you find in space. Now when you condense it, that comes down really quick, and you wind up with something that's like 2, 3, 4, 5 psi above absolute vacuum. So as much as about 10 or 12 psi below ambient. Now your vacuum doesn't suck, actually it's the pressure on top that pushes, and because the vacuum on top is pushing, that's atmospheric pressure, that's why these are called atmospheric engines. So until you could move to high pressure steam, if you were relying on creating a vacuum and then atmospheric pressure to push down, these were called atmospheric engines. Atmospheric engines it's a derogatory term, and it's not mutually exclusive to steam engines. When I say my car is a gasoline-powered internal combustion engine, my car is gasoline-powered, this is steam-powered. My car is internal combustion, this is atmospheric. You'll notice another thing about these shapes. The Haystack boiler is a sphere. Cylinders, of course, are cylinders. Structurally speaking, these are very strong in terms of pressure from the outside. As long as the pressure from the outside is even, cylinders and spheres can take on a huge amount of pressure difference. But when you create a higher pressure inside, they're actually fairly weak. And that's why these things could explode so easily. If you were to pressure them up to, say, 15 or 20 psi, you might blow it up over ambient. But you could generate 15 psi below ambient inside, and they were safe. So how much work can you actually get from one of these things? Well, the pressure, and we're going to talk in terms of psi because in this case it's actually a little bit easier. PSI is pounds per square inch, and it's literally pounds per square inch. So if your pressure difference between the top and bottom is 10 psi, which would be typical, if you have a little 1-inch piston with 10 psi pushing out, you can lift 10 pounds. So the formula is pi r squared. It's the area of a circle, since these are always round. So if you look at something like a 1-inch radius, the amount of weight you can lift with 10 psi, that's going to be 3.14 times 1 squared times 10, and that's 31 pounds. So what if you double that? You do a 2-inch radius. Well, that's 3.14 times 2 squared, or 4, times 10 psi. You jump to 126 pounds. You just jumped from 31 pounds to 126 pounds by going from here to here. So it's going up pretty quick. If you go up to an 8-inch radius, a little bit bigger than this, for the radius, now you can lift a ton. What if you go up to 11.25 inches? Now you're lifting 2 tons. This cylinder, the piston's almost 4 feet across. I think it's 46-inch. So that's a 23-inch radius. This thing can lift a ridiculous amount of water. And the capacity just keeps going up as these get bigger. That's why these things are all so ridiculously huge. Water's heavy, but as these get big, these engines could handle it. So before we move on to the next video, I just want to remind you to please like this video, like all the videos in the series. Also, if you have questions, comments, drop those down in the comment section of the video. I love reading the comments. I usually respond to them pretty quickly. So the next video, we're going to look at some more of James Watt's inventions. The external condenser was really what made his name. That was his big invention that everyone thinks of. But he actually made a lot of other inventions as well that were maybe even more significant in some ways. And he installed them on this. This is his 1811 canal pump, and it has a lot of extra features on it, not all of which make a lot of sense. But I'll let that video explain it. So let's go take a look at this James Watt 1811 canal pump, and then we'll meet back here and talk about why we aren't using atmospheric engines at all anymore.